Good afternoon and welcome to this NASA media briefing on an exciting new discovery at the edge of our solar system. This is Steve Cole from NASA headquarters in Washington, D.C. Today we're bringing you the latest results from our Interstellar Boundary Explorer mission. IBEX has been exploring the outer reaches of our solar system since 2008. The finding you're about to hear about today has just been published in the Astrophysical Journal. We have 4 scientists here today to talk to you about the new results. Let me introduce them to you. Our first speaker will be Dave McComas, who is the lead author of this new research and IBEX principal investigator from the Southwest Research Institute in San Antonio, Texas. Our second speaker is Eric Christian, who's IBEX mission scientist from Goddard Space Flight Center in Greenbelt, Maryland. Our third speaker will be Brenda Dingus, an astrophysicist at Los Alamos National Laboratory in Los Alamos, New Mexico. And our fourth speaker is Arik Posner, who's IBEX program scientist here at NASA headquarters. We'll start with remarks from each of our panelists and then open it up for a conversation with those watching online and media who are on the phone lines. If you have a question and are watching online, you can post it on Google+, on Facebook and YouTube, as well as on Twitter using this hashtag, AskNASA. Okay, let's start with our first speaker. Dave?
Yes, thanks, Steve. So we're going to talk about something really exciting today. Fundamentally, like a comet, our solar system has a tail. If we can go to the first graphic, you'll see a beautiful picture of Comet Ison. And the reason that comets have tails is because there's a 1,000,000-mile-an-hour solar wind blowing outward from the sun all the time in all directions, and it blows material from the comet that's coming off the comet away from the sun into this tail-like configuration. In addition to that, the solar wind inflates the area around the sun, something we call the heliosphere. So if we can move to my second graphic about the heliosphere, you'll see what this configuration looks like. So we're all the way on the inside there where you can see the sun in the middle, and the IBEX spacecraft that took the data we're going to talk about today is orbiting the Earth in very close to the sun. But out 100 to a couple hundred times as far away as the Earth is from the sun are the boundaries of our heliosphere, with the solar wind inflating the inside and filling the inside with material from the sun and material from the rest of the galaxy on the outside. You can also see the 2 Voyager spacecraft there, which are heading towards the interstellar medium, but haven't gotten there yet. Now, if you go to the third graphic, you'll see that we're not alone in having things like a heliosphere. When it's our own sun, we use the Greek word helios and heliosphere, but when we have these structures around other stars, we call them astrospheres. And here are 3 beautiful pictures of astrospheres around other stars. And what you'll see here is that there's a lot of variation in the types of structures that we see around astrospheres. Some of them have very strong shocks in front, some of them are misshapen and asymmetric. And in particular, the one on the bottom, which is Mira, has this very long and knotty tail which extends many, many light years away behind that star. And so the real question is, what's our own interaction look like, and do we have a heliotail? Does the heliosphere have a heliotail, and if so, what does it look like? So moving on to the video, I'll show you a visualization of this that ends in our data. So IBEX is in orbit around the Earth. As we back away, you can see the flow of the solar wind outward and then back down the tail. And this solar wind is colored 2 different colors here, red for high-speed solar wind at high latitudes and white for lower-speed solar wind at lower latitudes. So that's being pushed back around by our motion through the interstellar medium. There's also a magnetic field in the interstellar medium shown by these blue lines, which squeezes and misshapes our heliosphere, and the heliotail actually more than other parts of the heliosphere. So let's have a look at what the data looks like. We'll move back into the Earth, and if we were able to see these structures with our eyes, as we can in particles that we're able to measure with IBEX, it looks like this. And what you see here at low and mid latitudes are these 2 structures we call lobes. They're sort of red and yellow on the left-hand and right-hand sides. And then at the top and the bottom, the blue regions, is a faster solar wind, high-speed solar wind. And so the tail is full of solar wind, material that came from the sun, got bent back around, and goes down a long heliotail but it's ordered in this very interesting way with the lower energy, low speed wind at low latitudes and the higher energy, high speed wind at high latitudes. And I think you can even see a little bit of a tilt in the data here, but we're going to come back to that topic at the end. So with that, I would like to pass it over to Eric Christian, who's going to tell you how IBEX makes these incredible measurements. Eric?
Thanks, Dave. So most images you see coming from NASA and from things in space are make pictures with light. That's what you expect a camera to do. But IBEX uses an interesting thing called an energetic neutral atom. Most of the matter in the universe is charged. It has an electric charge on it. It's called plasma. And especially when it's moving fast and or is very hot. But if you go to the neutral particles video, when these charged particles, which get messed up by the solar magnetic field, the Earth's magnetic field, the galactic magnetic field, so you can't trace their direction back, but when they travel all the way out to the edge of our solar system, starting at the solar wind, some of them moving very fast, charged particles, pick up an electron from neutral gas that's out in interstellar space or in the outer heliosphere. And once it picks up, and here you can see has an interaction, picks up an electron, and once it picks up an electron and becomes an atom, a neutral atom, it travels straight. Some of those are pointed back at the Earth and come in and actually hit the IBEX spacecraft and get detected. So you can, because they travel pretty much straight, you can trace them back to where they came from and make a picture with these atoms instead of light. And that's what IBEX does. To tell us a little bit more about why understanding the shape of the heliosphere is important, I'm going to pass us to Brenda Dingus. Brenda?
Thank you, Eric. So I'm going to tell you a little bit about the importance of understanding this bubble that the sun creates around the solar system that IBEX has been teaching us about. And basically, this bubble, it is a shield for cosmic rays. So cosmic rays are actually what I principally study. And cosmic rays are radiation of very, very high energy particles. These high energy particles are made probably in supernova remnants. So this is an explosion of a massive star, and it creates a shock wave and accelerates particles to energies much higher than we can make on Earth in man-made accelerators. But those cosmic rays, when they hit this bubble, they're frequently deflected by the magnetic fields in the bubble because they are also charged particles, as similar to what Eric was talking about. So in the graphic, it shows as you get closer and closer to the sun, that line shows the fraction of the cosmic rays that actually make it into Earth. And this depends on the energy of the cosmic ray as to how much the magnetic field influences it. And so you can see that a lot of the cosmic rays are actually shielded by this bubble that IBEX has measured. And in particular, what we are seeing in high-energy cosmic rays is that there's something funny about the tail region, about the region opposite to the direction of the motion of the sun. And in that region, we have a slight fractional excess of cosmic rays, even from that direction, at higher energies than we think that the sun should influence it. And so I'm principally interested in this result to try and understand if the sun could possibly influence these cosmic rays at higher energies and how that actually works. And in particular, this region in the tail where the sun's influence is the least, could that somehow let in more cosmic rays or maybe focus cosmic rays from that direction? But it's a very small fractional increase that we're looking for there. Anyway, just in general, I think this is an exciting result that we are looking forward to thinking more about and its application to the study of cosmic rays too. So I'll pass it on now to Art Posner, who will tell you a little bit more about the IBEX mission.
Thank you, Brenda. So just as a context, the Interstellar Boundary Explorer is one of a long line of very successful Explorer missions. The Explorer mission line actually started, as you can see here in the movie, in 1958 and predates the agency. The very first discovery from space has been made with Explorer 1, that were the radiation belts, or now called Van Allen belts. There was a long line of these rather inexpensive missions For example, COBE, as you will see here, the Cosmic Background Explorer, which actually gained one of NASA's scientists a share of the Nobel Prize a few years back. And IBEX is one of the rather recent additions, I think number 91 in a total of 94 Explorer spacecraft. And as such, as this low-cost, inexpensive mission has made remarkable discoveries, including now the Helio tail. Here you see IBEX. Let me just add one more word. IRIS, the Interface Region Imaging Spectrograph, is our latest edition, just launched 2 weeks ago. It's such a baby that it hasn't even opened its eyes yet looking at the sun, and we expect new discoveries from IRIS as well. With that, I give back to Dave McComas, the IBEX PI, to tell us more about the twist of the Helio tail.
Well, thank you very much, Arik. Yeah, I'd like to come back to the issue that I mentioned earlier, which is if you look at our data, and here's another version of the data. What I showed previously is sort of the central circle in the top part of this figure. This figure actually shows the entire map of the sky in these energetic neutral atoms. Just like a globe can be made into a representation on a flat map on the wall, you can also take an all-sky map and make a representation like that. And so that's the representation you see at the top. But if you just sort of think about the middle part where the circle is as being on Earth and looking back down towards the tail, you see these two lobes with the red and yellow regions, and you see how there's a little tilt to them. It's not horizontal if you connect the centers of those. And that little tilt is a little easier to see in the bottom, where we've smoothed the data because the statistics aren't that great. Once you smooth the data, I think you can see very clearly this tilt. That tilt is a really interesting aspect of the observations. It has to be caused by something, and it can't be caused by the sun, which is basically symmetric with its own rotation axis. And so if you move on to the next graphic here, the twisted tail, you'll see how we think this twist is coming to be. You see the external magnetic field from the local interstellar medium. It wraps around the heliosphere and around the Helio tail. And I like to think of this as sort of a beach ball and bungee cords. If you imagine putting bungee cords, partway around a beach ball, or pulling on them, they exert a force, and that's exactly the same sort of thing that a magnetic field line does. It actually exerts a force. It exerts a force on the outer boundary of our heliosphere. That force both squeezes the Helio tail so that it's no longer circular in cross-section, but is actually flattened like an oval or an egg, but it also twists it and starts to turn it in the direction in which the forces are strongest, which is to align with the magnetic field. And so this schematic that we're showing here gives you an idea of how the strong interplanetary magnetic field, interstellar magnetic field, can actually twist and squeeze our Helio tail. And so with that, I think we'll go back to Steve and take any questions.
Okay, thank you, Dave, and thanks to all our panelists. And as Dave said, we'll take questions now. For media that are on the phone lines, to ask a question, just press *1. You'll get in a queue to ask a question. And for those watching online, all you have to do is on Twitter, use the hashtag #AskNASA. We'll also be checking the Google+, Facebook pages for your comments that you're posting there. Okay, our first question from the phone lines is from Irene Klotz. Irene, you can go ahead.
Thanks, Steve. Thank you for the briefing. I just was wondering if someone could please discuss what is new about these findings of the Helio tail compared to what was known previously, and also if you could specifically address this four-leaf clover structure and how that in particular might have been shaped by the magnetic field lines that you were just discussing. Thanks.
Sure, this is Dave. Maybe I'll take a cut at that and then others may have more to say. If we could go back to the heliosphere, number 2 figure that we had. So what's new about this is that we were never able to really look in the direction away from the direction that we're moving through the interstellar medium. And so in this graphic here, you see us there at the sun in the center, and imagine the sun is not moving, and we'll just take all the motion from the local interstellar medium. That would be flowing in from the left side in this figure and making the sort of bullet-shaped blunt structure that you see here for the heliosphere. We've had good statistics in IBEX over the last 3 years of observations, and we've filled in most of the sky map. But for reasons related to how we take our observations, there's been very poor statistics in one part of the sky, and that's the direction back down towards the Helio tail. By very carefully assembling the statistical observations from the full first 3 years of IBEX data, we've been able to fill in that direction. And in fact, it's an interesting story because not knowing what was back there, we'd seen a small structure that we were thinking might be the Helio tail, a very small structure that was offset to the side. And when we started studying that, what we learned was, in reality, once you had all the observations, the first 3 years of observations, and you filled in the hole that we'd had in previous sky maps, that actually the Helio tail was a much larger structure with this much more interesting sort of configuration. And that brings us to kind of the clover shape. Again, maybe we'll go to the IBEX data, number 8, plot for that. So again, looking in the center portion of this plot, this is really not expected. What we see here with the 2 lobes at low to mid latitudes, the yellow and red regions, is we see slow solar wind, very low energy particles and energetic neutral atoms coming back towards Earth and coming back towards IBEX from the Helio tail. And we see this high latitude, faster solar wind and higher energy ENAs coming back towards us. I think we can understand that in terms of the ordering of the solar wind around solar minimum, which has slower speed solar wind at low latitudes and higher speed solar winds at high latitudes. IBEX is actually observing ENAs that were probably born as solar wind particles 3 to 5 years ago in the Helio tail, maybe even longer. And so they represent an earlier time in the solar cycle, back more closer to solar minimum than the current solar maximum. So with that, was there anybody else who wanted to?
Yeah, I'd like to add something. So what I think is really new about this is that scientists had always presumed that the heliosphere had a tail. We've seen it around other stars. We know that the sun is moving relative to interstellar gas, and so we presumed there was a tail. But this is actually the first real data that we have that gives us the shape of the tail. We've never taken a picture of it. There are no spacecraft that are going down the tail. Pioneer 10 is heading in that direction, but got turned off because it ran out of power years ago. So this is really the first time that we have data that tells us about the tail.
Okay, thank you both. A follow-on question is the Helio tail. What do we know about how long it is, how big it is from these observations?
So the length of the tail is one of the things that we don't measure particularly well. Because we make line-of-sight integrated measurements from the inside looking out, they're not fundamentally easy to get the length. On the other hand, once you have direct observations of the tail, as we do now, and you know the energies of the particles, you're able to do some simple calculations of the length. And when we do that, it looks like the Helio tail is probably evaporating through this charge exchange process that produces neutral atoms, the ones that we observe when we look back at the Helio tail. Those also go off in other directions. And so this sort of evaporation of the charged particles occurs over probably something like 1,000 times the distance between the Earth and the Sun. That's some number like 100 billion miles. And so unlike the very long tail that we saw with Myra, the actual tail, especially of the charged particles behind the heliosphere, is probably significantly shorter. That said, there's probably a much longer wake region where particles charge exchange back and forth, and you get coupling between what was originally solar material from the heliosphere and the local interstellar medium.
Okay, we've got a number of questions from online. Here's the first one. Has IBEX data shed any light on what Voyager may find in interstellar space?
Wow, I guess I'll start. This is Dave again. I'll start on that one. I think IBEX has shed a tremendous amount of light on what Voyager may find. The original discovery, first major discovery of IBEX, was this ribbon of enhanced energetic neutral atoms emissions, which appears to be determined by the external magnetic field that's draped around the heliosphere. That direction, that magnetic field orientation, wasn't well known before IBEX. I think we've now made the best measurements of that. When the Voyagers finally get out into that region, I expect that we know a lot more than we did about what that magnetic field orientation will be. I think we also know a lot more about the strength of that magnetic field. Prior to IBEX, pretty much the entire heliospheric community believed that there was a bow shock in front of the heliosphere. Observations from IBEX both related to the magnetic field strength in the interstellar medium, and also new measurements from IBEX about how fast we're traveling with respect to the interstellar medium have basically allowed us to conclude that there probably is no bow shock in front of the heliosphere. And so the sort of material that Voyager should find when they cross the heliopause is somewhat different than people had predicted back when they thought there was a bow shock. Eric, sorry.
That's okay. Eric, do you have a follow-up? Okay. Here's a related question that came in from online as well. Will the IBEX and Voyager teams be working together, sharing data after Voyager leaves the solar system?
Absolutely. And in fact, a couple of the people on this press conference are involved with both of the teams. So maybe Eric or Arik would like to comment about that.
Yeah, let me just mention that heliophysics has an open data policy. That means after allowing the teams the necessary amount of time, we expect them to make all data public to everyone on the web, so everybody can look at the data and everybody can use it. And of course, that way there are lots of collaborations now already between the teams, also independent researchers. We have a number of grants programs that fund, for example, modeling of this interstellar interaction. And with all the data combined, they have a much better idea now than 5 or 10 years ago how the physics of this interaction actually looks like.
And if I can add something, I mean, I did my PhD thesis using the Voyager data and still work very closely with the project scientist for Voyager, Dr. Edward Stone. And there are Goddard scientists who look at the Voyager magnetometer data, so we talk with them regularly. And so this is important to both missions. And so there's pretty close contact.
Yeah, I guess I might just add one more thing. We've already had one joint meeting, I think it was back in 2009, shortly after the first IBEX results came out. And Ed and I talked about having another meeting where we put the two teams together and see what synergies come out of that combination.
Maybe I add another thought here. It's maybe not that clear, but heliophysics is actually a system science. So you don't only have IBEX and the Voyagers, you also have continuous surveillance of the sun. Actually, when the sun coughs or has any sort of eruptions, we now can see it from all sides. We have the stereos from the backside. And these actually have influence on the interactions with the interstellar medium. So we really have a systems view that we can put together, that the scientists can put together and really advance the understanding of this entire region from the sun, from the core of the sun, out to the interstellar medium.
Okay, thank you. Reminder for those watching online and for the media. The media on the phone lines, if you'd like to ask a question, just press *1. And if you're watching online and want to ask a question, just use the Twitter hashtag #AskNASA. We have several more questions here. Let me go to the next one. This is, I guess, for Eric. How long is the IBEX mission expected to last?
You mean Arik this time? Sorry.
Arik, yes, Arik, I'm sorry.
We have regular senior reviews as they are mandated to us, which look into the performance of the mission teams and their assigned strategy for the next 2 or 3 years. And we just completed one. The results have been published, and IBEX has been extended by 2 years. So I think currently it will run through 2015 or 2016, and then we will have another evaluation and see whether the performance stays up or there are new opportunities we can pursue.
Okay, thank you. Here's another question from online. What are the physical properties of the heliosphere as compared to the interstellar space? How do you differentiate those two physically?
Eric, Christian,
maybe
you want to take a first cut at that?
Sure. So this is a really interesting topic at this time because Voyager is on the very edge of our solar system going up towards the nose, towards the direction that the sun is traveling. And we were expecting one sort of edge, and we're not quite seeing that. There are particles that come from the sun, there's a magnetic field that comes from the sun, and there are energetic particles that are generated in the outer heliosphere that we expect to all fade away, and what you're going to see are the particles and magnetic field of the galaxy, interstellar space. Voyager 1 is almost certainly going to be our first interstellar probe. But this boundary is a lot more complicated than...
I think
looks like
we lost Eric.
But maybe I can, maybe.
Yeah, Dave, please pick it up.
That's okay. Eric's back. He can take it.
Eric, are you back? And Eric, you're
I'm
muted,
back.
I think.
Yep. So,
okay, perfect.
So one of the reasons why we think that Voyager is still inside the heliosphere, despite the fact that the particles actually look more like interstellar space than solar system, but the magnetic field that Voyager is seeing currently still looks very much like a solar magnetic field. The direction, the strength match what we expect from the sun and what it's been seeing since it got launched more than 35 years ago. So the big clue to when Voyager leaves the solar system and enters interstellar space, we expect, is the magnetic field. And IBEX has been an important part of knowing what sort of field we expect out there.
I guess I'd make a further comment. Since a number of the questions have sort of been related to Voyager and IBEX and how they interact, can we go back to the heliosphere graphic number 2? I think about these two missions as incredibly complementary, and in fact, the analogy that I always think of is IBEX is really like in a medical situation, like an MRI, where you can take an image of the entire part of the body that there may be something going on with and understand the big picture of it. Whereas the Voyagers are very much like biopsies; they're extremely precise local measurements, but they're only at one or two very specific locations. If you look at this graphic of the heliosphere, you can see what I'm talking about. Voyager 1 and Voyager 2 are headed out towards the nose. One's about 30 degrees north, one's about 30 degrees south, and a little bit off to the side. But neither goes at all back towards the heliotail, let alone, or the flanks or any of these other directions. And so while we have incredibly good and valuable information from those two locations where we have those spacecraft, how you put those into a global context and understand the really three-dimensional global interaction of the sun with the local part of the galaxy is really more a job for IBEX, which looks out all directions in space and takes the entire global image, admittedly from the inside looking outward, but still takes the entire global image. And so it's really the combination of those two together that's dynamite in terms of really figuring out this very complicated and difficult interaction and allowing us to explore both directly with in situ measurements and remotely with these global observations, our place in the galaxy and our interaction with it.
Maybe I can add a few words to that. Last year, 2012, was a very big year for heliophysics at NASA. The National Academy of Sciences has published its 10-year or decadal survey report on the strategic outlook for our science. And it recognized actually the progress being made in the understanding of the interstellar medium interaction with the heliosphere as one of the 4 major science goals that they expect to NASA look into in more detail. And one of the outcomes of this decadal survey, and here at SMD at NASA headquarters we take this advice very seriously, is a recommendation of a future, beyond the current program, possibly a future mission that would actually take a little larger scope than IBEX has. As I mentioned, IBEX was a rather inexpensive mission. It's in an Earth orbit. To go a little further, take the next step, build additional or complementary instruments and place it somewhere where it's better suited to even look into this interaction in more detail. And actually, it might be possible with that new mission in the next decade or so to see the changes also, not only a picture like we just did now, but the actual changes driven by the sun or other interactions maybe from the outside, and see the evolution of this interplanetary interaction with the interstellar medium.
Okay, thank you. Getting back to IBEX, a question about the mission and its future. This result is based on the first few years, I think the several years of data from IBEX. Dave, what do you expect to learn about the Helio tail from continued observations going forward from IBEX?
Sure. So as I mentioned earlier, IBEX basically sees solar wind that was produced years earlier, traveled outward from the sun, got bent back around from whatever directions it was traveling towards the Helio tail, into the Helio tail, and down the Helio tail. So we're sampling much older times, and we see evidence in our data of the structuring which occurs at the minimum of the solar activity cycle, where you have fast solar wind at high latitudes and slower solar wind at low latitudes. During solar maximum, that structure breaks down, and we're going through solar maximum now, basically, last year, this year, maybe next year, we don't really know. But that structure basically breaks down. The inclination of the heliosphere current sheet becomes quite large, as it already has, and the solar wind is no longer so simply ordered by latitude. Over the next number of years, those particles will travel out and be bent back and head down the Helio tail. And so our expectation is that we should be able to see the effect of the changing sun and solar wind on the Helio tail structure over time. We hope to do that with IBEX. And if IBEX stays healthy, which it has so far, it was only designed for 2 years, but it was launched in 2008 and we're still going strong. If IBEX continues to be healthy, and if there's funding through the decadal survey process that Arik was talking about, we hope to be able to make those measurements with IBEX. However, we're also incredibly excited about the possibility of an even better set of measurements from the new IMAT mission that he was talking about, that Arik was talking about coming out of the Heliophysics Decadal Survey. That would be just an incredibly exciting mission with much better sensitivity and resolution, and carry on the work of IBEX even better than IBEX is able to itself.
Just a minor correction, the IBEX funding comes through the senior review process, not the decadal survey process.
Oh, sorry. That was a speak
Okay.
of.
And if I could add something, one of the interesting things about the continuing with the IBEX data is that, as Dave said earlier, IBEX essentially sees a line of sight. It sees everything in a given direction. And so as the sun gets more active, as the solar wind structure changes, we can see those changes in the IBEX map. And the timing of that, because these particles take years to get out there, the timing of it is actually a good way to tell exactly where these energetic neutral atoms are being formed, and give us a lot more information about the IBEX data and what's going on in the heliosphere.
Another question about IBEX. This has to do with how it does its detecting of this kind of feature. Does IBEX pick up the charged particles of cosmic rays, or is it limited to solar particles?
Well, IBEX doesn't directly measure charged particles. It measures neutral atoms produced through charge exchange. Primarily, those neutral particles were originally from the solar wind, but not all of them. Some of the interstellar material, which is originally neutral, comes floating into the heliosphere and gets picked up by the solar wind, gets ionized and charged, starts gyrating around the magnetic field in the solar wind, is carried out, and can be neutralized again through charge exchange, producing energetic neutral atoms. And so IBEX doesn't differentiate between those two. It observes all energetic neutral atoms that happen to be heading back in towards the Earth and towards the spacecraft. That said, they have different sorts of energy distributions, and because IBEX isn't simply taking a picture of energetic neutral atoms at one energy, but actually differentiates energies all the way from about 10 electron volts all the way up to 6,000 electron volts, we actually make these measurements as a function of energy, and we're pretty well able to separate the source of different ENAs, whether they came from the sun and solar wind originally, or from pickup ions or something else.
Okay, thank you.
Yeah. And I'd like to add something quickly.
Yeah,
so IBEX also measures the neutral atoms that are coming directly at us from the interstellar medium. Most of the interstellar medium is ionized, and that gets pushed out by the magnetic field and flows around our solar system. but some of the gas that's outside of our solar system in the galaxy is neutral, and that flows straight into the inner solar system, and IBEX has made some really interesting results from that interstellar neutrals that come in.
Okay, thank you. Brenda, this is a question for you about galactic cosmic rays. You had talked about the focusing that might be happening in the direction of the tail. Can you talk a little bit more and tell our viewers a little bit more about how galactic cosmic rays get into the solar system from different directions?
Sure. So the galactic cosmic rays, they are influenced by the magnetic field outside our solar system, which is one thing that IBEX is telling us what the magnetic field is like just outside our solar system. But then they're also in this magnetic turbulence that's created by this bubble will deflect the particles. Just kind of like we see on the Earth, we see particles coming in, these cosmic ray particles, and they're affected by the Earth's magnetic field, and you can see the aurora at high galactic latitudes. But at the equator, you don't. So basically, a particle cannot cross a magnetic field line very easily. But the more energy the particle has, the less that magnetic field matters. So the higher the energy of the particles, the more they just blast right on through. And the cosmic rays at really high energies are isotropic. They come from almost all directions equally. But as you go to slightly lower energies, we're starting to see this non-isotropic distribution, meaning that they're coming from some directions preferentially. And a few may be coming in from the look like they're coming in from the direction of the helio tail. And that would be where the sun's influence is the least, because it's the farthest away from us. And so maybe that's why we're actually seeing an excess of cosmic rays. But we don't know exactly what the situation is, and it's actually pretty hard to influence such high energy cosmic rays with the solar field. So it's a question that's going to require some theoretical work to take the IBEX results and the cosmic ray results and put them together and try and see if it holds, if it makes sense. And that work hasn't been done yet. This is a very new result.
Okay, thanks, Brenda. A reminder for those watching online, you can ask a question. We still have several more to go here by using the hashtag AskNASA on Twitter. And if you're media on the phone lines, just press *1 to ask your question, and we'll get you in the queue. Here's a general question. Throw it open to the group. Is the heliosphere like the Earth's magnetosphere? How do they differ? How are they similar?
Like the Earth's magnetosphere. Yes, in some ways they're similar. In the case of the heliosphere, it's the sun's magnetic field and the sun's plasma that inflates the heliosphere. In the case of the Earth's magnetosphere, it's the Earth's magnetic field and a mixture of the Earth's plasma and plasma from the solar wind, which fill the magnetosphere. In both cases, they basically exclude most of the material coming in from the outside. In both cases, there's a relative motion between, for the magnetosphere, the solar wind blows towards the Earth. In the case of the heliosphere, we move through the local interstellar medium. But in both cases, you end up with structures that have this sort of blunt shape on the nose, and now we know an extended heliotail to go with the magnetotail on the downwind side. But there are also some significant differences, certainly in the size and scale of these structures, heliosphere being immensely larger than the magnetosphere. Did somebody else want to comment on that?
Yeah, I'll just add a little bit that the whole sort of shape of the magnetic field inside the heliosphere is different than the shape of the magnetic field inside the magnetosphere, mostly because of the solar wind. The solar wind, as it travels out from the sun, drags the magnetic field out with it, and actually, because the sun is rotating, causes the magnetic field to have a spiral pattern, what we call the Parker spiral, whereas the Earth's magnetic field is much more like a dipole, like you get from a standard bar magnet, with a tail. The Earth has a magnetotail that drags behind it. So.
Okay, thank you. The question referring to those astrosphere images for around other stars that we were shown earlier. In a simple language, how would you describe the shape of Earth's heliotail? I'm sorry, of the entire heliosphere. We see some there that look like broad fans. Some are long, elongated tubes. How would you describe the shape of our heliosphere?
Well, I think what we've learned from IBEX is that it is bullet-shaped, likely bullet-shaped, and this is not just from IBEX. This is from IBEX plus a lot of theory and simulation, and including the Voyager results. So pulling all that together, I think we see the heliosphere as bullet-shaped on the front, and now we understand that it's got this heliotail that extends back probably something like 10 times further than it is towards the noseward direction. So quite long, fairly long, kind of bullet-shaped. But that bullet isn't symmetric. It's actually misshapen by the external magnetic field. There's probably additional fine structure, waves on the surface and on the boundaries. We don't have the resolution and sensitivity with IBEX to pick those sorts of fine structures up, although a follow-on mission like IMAP should be able to do that. But it probably doesn't look very much like any of the three images that you can see in this in the astrospheres graphic. If you put that back up, probably doesn't look very much like any of those. Maybe the most like the right-hand portion of the bottom one, Myra, with sort of a kind of a longer tube going back from a sort of bullet-shaped front.
And a related question, how will these IBEX observations help us learn more about the tails around other stars?
Well, I think there's a huge opportunity for sort of comparative heliospheric and astrospheric observations. I mean, we really have a lot of detailed information now with IBEX and the Voyagers about our heliosphere. On the other hand, we get these beautiful pictures from the outside of the astrophysical objects. And so it's always been one of my dreams with the IBEX mission that we would be able to get the astrophysics community more engaged with the IBEX results and see if we can work together on understanding how the detailed information that we get from our own heliosphere helps inform and understand this menagerie of different sort of astrosphere type structures that we observe around other stars. Did anybody else want to comment on that?
Okay. Okay. Another question from online. What institutions are involved with the IBEX mission?
Yeah.
if it's a huge list, we can refer to it online.
It's a long list, and we certainly should put it online. I'm afraid to start giving a list and leave somebody important out off the top of my head. The IBEX mission is led by the Southwest Research Institute in San Antonio, Texas, with strong partnerships from a bunch of other institutions: Los Alamos National Laboratory, University of New Hampshire. We even have international collaborations. The University of Bern, Switzerland, contributed hardware, and a number of many other places. There are a lot of institutions with scientists who are involved from across the country and around the world. And so it's quite a long list, and I'd like us to post that so that we're sure everybody gets the credit they're due.
Right, and we can refer people to the website in a minute. I think this is our last question. Dave, this is for you. What IBEX discovery of the many that it has made so far has surprised you the most?
That's a really interesting question. There have been so many great surprises with IBEX, and it's amazing when you. I feel like we've had the first telescope to look out into the skies with. I mean, you almost feel like you're Galileo and living in that era. We have the first really good high sensitivity energetic neutral atom imaging telescopes to look out with, and we've made so many discoveries with those that they're really hard to compare. I mean, the ribbon was completely unexpected by any of the theories or models before the IBEX results. the fact that there's no bow shock, the fact that there's this complicated helio tail behind us, the measurements, the direct measurements of the interstellar material, where we're able to actually get the composition of it and show that it's not exactly solar-like in some ways. I mean, there's just such a long list of those that it's hard to pick a favorite. It's like all my children are wonderful.
Understood. Okay, well, that's the last question we have. So thank you to all our panelists, and I wanted to let everyone online know that they can continue to follow the IBEX mission, find out about some of its previous discoveries online at www.nasa.gov/IBEX. And please continue to follow NASA Science, NASA Heliophysics on the variety of social media channels that NASA has available. They're all listed here. And thank you all for watching. Thanks to our panelists, and we'll see you next time.